chapter to go to here. And our first topic of discussion, we're going to sort of stray away from what we had learned about aldehydes and ketones previously with that electrophilic carbonyl carbon. And we're going to kind of build off of that, learning about a new set of reactions. The first type of compound we're going to look at are what are called alpha, beta, unsaturated. Oh, shucks. Unsaturated ketones and aldehydes. Okay, so first of all, if we take a normal old aldehyde or ketone, they have this lettering system where as you start moving away from that carbonyl carbon from those functional groups, they label these they label these carbons with the Greek alphabet. So the first carbon would be the alpha carbon, then the beta carbon, then the gamma carbon, then the delta carbon, and then epsilon, etc., etc. So an alpha beta unsaturated ketone or aldehyde means that we have between our alpha and beta carbons, we have a double bond, right? A degree of unsaturation. So this would be an example of an alpha beta unsaturated, in this case aldehyde. Okay, and they also have like one of those little fun slang names. In this case, they call them enones. Right? One is that ending for a ketone. Actually, regardless of whether it's an aldehyde or a ketone, they just kind of have this slang term enone. Right? So we have a double bond next to our carbonyl group. Okay? And what we had learned about our regular aldehydes and ketones was that they have this very good electrophilic carbon, right? Both because of that polar bond where the oxygen is pulling electron density away from that carbon, but also because they have that good leaving group, that pair of pi electrons, right? So both of these make our carbonyl carbon an electrophile. All right, so now obviously our alpha beta unsaturated aldehyde, in this case aldehyde, or our enone, also has that carbonyl carbon, right? So it also has that same polar bond and that same good pair of leaving group electrons, that pi bond. All right, but let's draw this intermediate here that we get when we take that pair of electrons away from that carbon and place them onto that oxygen. All right, now we have our negative charge on our oxygen and a carbocation on that carbonyl carbon. But everybody take a second. This structure also has an obvious resonance structure because of that allylic carbocation. So take a second and draw me that resonance structure. So that allylic carbocation can accept that pair of pi electrons. And so we have this other resonance structure. Where now that positive charge is not sitting on that alpha, on that carbonyl carbon, but on that beta carbon. Remember, we would number away here, so this was the carbonyl alpha beta carbon. So these alpha beta unsaturated aldehydes and ketones, or enones, they have not just one, I mixed my charges up here, not just one, but two electrophilic sites. All right, our carbonyl carbon and that beta carbon. Okay, so that means that if we take one of these enones, let's just keep this same example that we've been working with. And we react it with a nucleophile. There are two possibilities. It could react with either one of those two electrophilic sites. So we could have that reaction that we've been seeing over and over again, where the nucleophile reacts with the carbonyl carbon. This will create an alcohol group from that existing carbonyl oxygen. As well as our nucleophile added on. These are nucleophilic addition reactions added on to that carbonyl carbon. So this would be the reaction at the carbonyl electrophile. Or it can react with that beta carbon, which is also a nucleophilic site. And we would retain that carbonyl bond. We would then just lose our double bond, our alkene bond. So this reacts at reaction at our beta carbon electrophilic site. All right, so both the carbonyl carbon and the beta carbon can play the role of an electrophile in these alpha beta unsaturated aldehydes or ketones, or enones as they're called. Okay, which one a nucleophile prefers tends to be a little bit of a tricky situation. It's hard to find sort of a rhyme or reason behind it. Like nitrogens tend to prefer the beta carbon, but other nucleophiles tend to prefer the alpha carbon. But there's one set of reactants that will really reliably react with one site or the other very specifically. And these are our organometallic reagents. Okay, so organometallic reagents. Okay, and these are two that have been introduced before. One of them we've already discussed quite a bit in this semester. Those are our Grignard reagents. Right, that name organometallic, there's an organic and a metal in the same compound. Our Grignards were one of those compounds, right, that MgBr. Okay, and it turns out that our Grignards in these alpha beta unsaturated ketones or aldehydes will really reliably react with that carbonyl carbon. They will not react with the beta carbon. Okay, so these react with the carbonyl carbon. Okay, the other one was introduced last semester. We have yet to talk about it this semester. This is what's called a Gilman reagent. Again, we have this organic molecule attached to a metal, an organometallic compound. In this case, it's copper lithium. The one thing about a Gilman reagent is just like a Grignard, they create a new carbon-carbon bond. And only one new carbon-carbon bond, but in your formula for your Gilman, there are actually two of those R groups attached. Only one of them will ever react with your molecule, but that's how the formula for a Gilman looks. And unlike a Grignard reagent, Gilmans will specifically react with that beta carbon. Okay, so both of these reactions are creating new carbon-carbon bonds, but at different sites within our alpha-beta unsaturated ketone or aldehyde. All right, so then let's just do an example here. Okay. All right, we have an alpha beta unsaturated, in this case, ketone. And first we're going to react it with an ethyl Grignard. We follow these up with some source of proton. And then we're going to do the same thing, but with an ethyl Gilman. All right, and again, these formulas look a little weird, but it's the organic molecule inside the parentheses here, these two carbons. These are what are going to be reacting with our enone. All right, so given what we just discussed about the specificity of these two reagents, give me my product here. If we're being good, these also have some source of proton that you need at the end. Okay, but importantly, our Grignard reagent will have our two carbons attached to the carbonyl carbon in our molecule. All right, and so when it reacts with that carbonyl carbon, what's going to be my functional group at the end here? An alcohol. So that carbonyl oxygen is still on there. It's an alcohol group. And now I have this ethyl group also attached, so specifically at that carbonyl site. Okay. And then our Gilman reagent will have these two carbons added specifically to our beta carbon. Okay, so now we have an ethyl group on our beta carbon. All right, and just to be clear, I formed two new bonds in this second reaction, this Gilman reaction. A carbon-carbon bond. What was the other bond that I had to have formed? Yeah, right. So if I look over here, there's only one hydrogen. On this one, there's two. All right. So just don't forget about our implied hydrogens here. So we also had to form that new carbon-hydrogen bond as well. Okay, cool. So anyways, we have these enones, these alpha-beta unsaturated aldehydes and ketones. They have two electrophilic sites. For the most part, it's kind of a crapshoot as to where your nucleophile is going to react, unless you're specifically talking about these organometallic reagents. These are very, very reliably going to select one of these electrophilic sites or the other. Grignard reagents will select that carbonyl carbon, whereas Gilman reagents will select that new nucleophilic, or no, new electrophilic site in our molecule, that beta carbon. Okay, so that was kind of a special class of aldehydes and ketones that we wanted to consider. We're going to learn by the end of the day today how to make these here, so it's a good thing to keep in mind, learn how to make these enones. But the next way in which we're going to talk about aldehydes and ketones is sort of very different. We've been talking about them always as electrophiles up until this point. Okay? Now we're going to start talking about what's called the alpha carbon, which we sort of introduced before, and its acidity. Okay, these concepts of acids and bases are really important in chemistry. Remember, you first were introduced to them in general chemistry. An acid plus a base makes a salt in water, and then you expanded upon it a little bit in Chem 1B when you learned about pH, and then we talked about it again in the first semester here. So it's a really fundamental principle in chemistry here. So what the heck do I mean by alpha carbon acidity, right? So acidity, important, means like the ease of removing a proton, right? Acids donate protons, and we talk a lot about removing protons from things. So for example, alcohols, we can turn into great nucleophiles, and bases, alkoxide ions, by removing protons. Okay, so this is just a really important thing to have nailed down. I know we covered it last semester, but make sure that you're keeping that sort of in your mind, because it's really important in terms of understanding things. And this is a great example. We're going to learn how to understand these reactions of aldehydes and ketones by looking at the acidity of an alpha carbon. All right, so let's just remind ourselves what an alpha carbon is. At the very beginning, we talked about how we have this labeling scheme for our aldehydes and ketones. Okay, so if I'm talking about the alpha carbon acidity, I'm talking about removing these hydrogens here. This is my alpha carbon. These are my alpha hydrogens. And it turns out that these hydrogens right here are actually relatively acidic. All right? We're using this, caveat relatively. Kind of think on par with like an alcohol. Not like crazy acidic, all right? But still somewhat easy to remove, which is kind of bonkers because they're attached to a carbon, right? Carbons are very, very reluctant to give up hydrogens. So these hydrogens right here that are attached to a carbon are actually relatively acidic. It's noteworthy here, something we haven't seen before. And I just want to point out something that I pointed out at the very beginning, but I just really want to stress here about these aldehydes and ketones. Aldehydes also have a hydrogen that's directly attached to the carbonyl carbon. This one right here is not at all acidic. I'm not talking about removing the hydrogen from the carbonyl carbon. I'm talking about removing them from the alpha carbon. Very, very important to keep in mind. Okay. So what do I mean by relatively acidic? So for example, an aldehyde, its alpha carbons tend to have a pKa of around 17. Ketones tend to be a little bit higher. Around 19, right? I said like on par with an alcohol. An alcohol has a pKa of around what? Does anybody remember? Around 16, which is the same as water. Okay, so that gives you an idea of where the kind of baseline is. Okay. In contrast, something like a carboxylic acid these have pKa's of around 5, right? So these are good acids that can actually change the pH of a solution. So again, our aldehydes and ketones, nothing too crazy in terms of how acidic those hydrogens are. But again, just to put it in perspective here, if I had an alkane, all of a sudden the pKa is around 60. Ridiculously difficult to remove hydrogens from carbons, except for these aldehydes and ketones, right? All these other functional groups here, these the hydrogens are attached to oxygens. We're talking about removing hydrogens from carbons, and because they're right next door to that carbonyl carbon, they tend to be relatively acidic, okay? We could even have a dione, a molecule that has 2 ketone groups in it. And if we were to look at the alpha carbon that's in the very middle here, that's sandwiched between those 2 carbonyl groups, those pKa, this pKa, because it's between 2 of them, would be around 9. So pretty easy to remove, right? Something even just like sodium hydroxide would be able to, with 100% efficiency, get that thing off of there. So that's pretty good. Okay, so anyways, let's think about it. Why the heck are these alpha carbon hydrogens so easy to remove, even though they're attached to a carbon? So let's do a simple acid-base reaction here. Take our friend acetone. And again, we're talking about this alpha carbon hydrogen. So here's my alpha carbon with its hydrogen. We're going to use a really good base here because, again, this pKa is on the order of 18, so it's not like sodium hydroxide is going to be able to do it. We'll use these amides here. Okay, and everybody take a second and draw me my acid-base reaction product here. All right, so remember, acids donate hydrogens, and bases accept those hydrogens. I need this to be just common knowledge for y'all at this point in your chemistry careers. I'm gonna have a hard time passing somebody that doesn't know what an acid and base are, right? So we gotta know in these reactions, our base accepts protons, and our acid is going to donate, get rid of that proton. Okay, so when that proton is snatched from that acid, it leaves behind that pair of electrons. And now my base has accepted that proton to become ammonia. So the bottom line here is when our aldehyde or ketone donates that hydrogen, it plays the role of an acid. That's what we're talking about, these relatively acidic alpha hydrogens. It leaves behind this carbanion, okay? Now remember, when we were talking about acid strength, we're like, how do we compare two acids? We said we don't look at the formula for the acids. We look at the formula of the conjugate bases. And we ask ourselves, how stable is that conjugate base? Because a nice acid has a stable conjugate base, right? What makes HCl such a good acid? The fact that the chloride ion is so stable all by itself. All right, so what we want to do is look not at our aldehyde or ketone to understand the acidity, but to look at its conjugate base, this thing right here. Okay, so why is this thing so stable? Well, take a second and draw me my resonance structure that is available to it because I have this allylic lone pair. Alright, so this pair of electrons comes down here, kicks that pair of electrons up there. Boom. Right, so we see that our conjugate base is resonance stabilized because it's located right next door to that ketone group. Right? So we have this stabilization of this negative charge. Okay, this thing right here, and there are these two resonance structures. This right here is what we call an enolate. Okay? And importantly, when we say an enolate, we're talking about either of these structures. You know, this is something that even I have a bad habit of doing, is we look at these resonance structures and we imagine that this molecule is like bouncing back and forth between these two, right? That's not true. It's both of these structures are true at the same time. You kind of got to blur your eyes. It's somewhere in the middle of this at all times. So when we say an enolate, I'm not referring to one or the other. I'm referring to this molecule right here, which is going through these two resonance structures, these two resonance contributors. Okay? So out of these two resonance contributors, which one do we think is the more stable of these resonance structures? Everybody take a second and look. We think it's the one on the left or the one on the right? Let's take a vote. Who thinks that the one on the left would be the more stable? And what about the one on the right? Why the one on the right? Negative charge on the more electronegative atom, right? Absolutely. So this is the more stable of our resonance structures. All right, but we have to be careful because this one, in a lot of ways, is better at explaining the chemistry of these enolate ions, because this site right here, with all this electron density, is going to play the role of what? A nucleophile or an electrophile in a reaction? A lot of electrons. What a nucleophile, which one has a lot of electrons? Nucleophiles or electrophiles? Nucleophiles, right? So, this thing right here is going to be our nucleophilic site. Okay, and I just want to stress this because we have definitely seen these alkoxide ions play the role of nucleophiles before. That's not unheard of at all. But it turns out that in these molecules here, in these enolate ions, it's this alpha carbon that we're going to see playing the role of our nucleophile. And that's really the key to this alpha carbon chemistry here. All right? We're going to spend actually all of next week as well talking about alpha carbon chemistry. We're going to introduce a few reactions here today, okay? And then we're just going to kind of keep on going because it's a rich field here. Okay, so first of all, before we start talking about this alpha carbon chemistry, let's just take a step back and make a note that this is going to be sort of a signature of aldehyde and ketone chemistry. The fact that we have both our carbonyl carbon, which is a good electrophile, but we also have this alpha carbon that's relatively acidic and can be turned in to a nucleophile. So aldehydes and ketones have both electrophilic and nucleophilic sites. We spent all last week and this week talking about the electrophilic sites, right? That electrophilic carbonyl carbon. Now we're moving on and talking about this nucleophilic site, this nucleophilic alpha carbon. All right, so alpha carbon chemistry. That's what we're talking about. Okay, so the first thing we're going to talk about with regard to alpha carbon chemistry are alkylation reactions. All right, so we're going to take an aldehyde or ketone. I'm going to put down an example here. All right, and the first thing that we're going to do is we're going to treat this with a good base. And for right now, I'm just going to say base. We'll talk about the identity of the base that we like to use in these and similar reactions next time. But for right now, everybody take a second and draw me that enolate ion that we would get when we treat this thing right here with a nice strong base. All right, so we need to have our anion on that alpha carbon. And remember, this is then in equilibrium with that other resonance form where that negative charge has now bounced all the way up to that oxygen. Okay, and now we have this carbon-carbon double bond. Okay, so now we're going to take this thing and we're going to do our alkylation reaction by mixing it with a alkyl halide. Okay, so we'll just use a simple alkyl halide. Alkyl halides are, of course, good electrophiles because they have that polar bond to that carbon, as well as, let's see, a good leaving group. Okay, so let's use this resonance structure here. We're actually going to practice our mechanism with both of them, but this one's a little bit easier here since it shows the negative charge on that nucleophilic site. Okay, so everybody take a second and see if you can predict what the product would be given what we know about these two reagents. All right, so what do we know about alkyl halides? Again, they are good electrophiles. And what did we just learn about these enolates at the alpha carbon? That they are good nucleophiles. And so nucleophiles and electrophiles are going to do what they do. The nucleophile is going to attack that electrophilic carbon, kicking off that leaving group. Okay, leaving us with an alkylated, an alkyl group on that alpha carbon, right? In this case, a methyl group. Okay, so now we're going to do the same thing, but with the other resonance contributor from our enolate ion, right? These are both the same molecule. All right, we got to make sure to wrap our heads around it. These are not two different molecules. These are the same thing, which means that if I start my reaction mechanism, I am going to get the exact same product. All right, so to be clear, what would be wrong is to look at this here and say, okay, now it's the oxygen that's going to be doing the attacking. No, no, no. We got to get the same product as we used with our other resonance contributor. Okay? So everybody take a second. See if you can go from A to B here. How do we get from our enolate ion to our product? All right, so here my nucleophile is going to be that pi bond pair of electrons. And that's not too crazy. We've seen pi bonding electrons playing the role of a nucleophile plenty of times. Okay? Now, importantly, I can't just draw that one arrow or I'd be left with a carbocation in this as well at my, what is like a carbonyl carbon, right? So all in one shot, this pair of electrons is going to come down at the same time that that pi bond is reaching out and reacting with that carbon. All right, so this is how I get my same product regardless of which resonance contributor I use for my enolate ion. Okay, because again, I'm making a really big stink about how these here are the same molecule, what we call that enolate ion. Okay, cool. So the next reaction that we're going to learn about is what's called a Claisen addition and condensation. These are two very closely related reactions. Hold on, okay. I almost botched that. Claisen is actually a different one. Sorry. We are going to learn about those, but first, we don't want to jump in too far. We're going to do what are called aldol addition and condensations. My bad. The Claisen ones are very similar, but we want to do these ones first. Okay, so the basis of these here are going to be what we talked about how these molecules, these aldehydes and ketones, have both a nucleophilic and an electrophilic site all in the same molecule. All right, so what we're going to do is we're going to take our aldehyde and ketone. Let's just use a simple aldehyde to start out with here. All right, so we got a beaker of this ethanol here, and we're going to put in a little bit of base. We'll talk about the amounts and everything like that next class. We're just going to kind of worry about our products here, okay? And what we're going to find is that neighboring aldehydes are going to react with one another, okay? So within our beaker here, when we draw this on pencil and paper, we kind of forget that we're not just looking at one molecule, right? We're looking at like billions in this little flask that we have when we carry out these reactions. So in this case here, I'm going to draw two of my same aldehydes here, because I'm going to make a point that one of them is going to play the role of the nucleophile, and the other one in this reaction is going to play the role of the electrophile. All right, so I got two neighboring molecules reacting with one another. They're both the same molecule, but they're going to play different roles in this reaction. Okay, importantly, which carbon is my electrophilic carbon? So the electrophilic carbon is that carbonyl carbon. The nucleophilic carbon is my alpha carbon. All right, so again, one of these molecules is the nucleophile, one of them is the electrophile. Importantly, the electrophilic site in an aldehyde is that carbonyl carbon, and the nucleophilic site in that molecule is this alpha carbon. Okay? So in this reaction, the first step is going to be to deprotonate that alpha carbon, right? So now my nucleophilic carbon has that net negative charge, and it's ready to go ahead and react with that electrophilic carbon. Okay, so my nucleophile is going to attack my electrophile. What else am I going to have to draw in arrow-wise at this step here? My nucleophile attacks my electrophile. What else is going to happen? I got to kick that pair of electrons up onto that oxygen, right? Just like we've always seen. Over and over and over again, we see this when our carbonyl carbon gets attacked. Boom. Okay, so everybody take a second and draw me this product right here with these two molecules connected together. right, so I'm going to start by drawing my nucleophile. Now I've gotten to my alpha carbon here. So when I draw that next bond, it's going to be connected to that new electrophilic carbon. Sorry, let me try to shrink this down so I got some room. Right, so now my new bond on the other side has to be that carbon I colored in orange, my electrophilic carbon. Okay, I still have that oxygen, draw it with a negative charge, as well as that other carbon from my electrophile. All right, so if I'm going to go in and color and be good and sort of keep track of who's who here, I have my 1, 2 carbons from my nucleophile in blue and my 1, 2 carbons from my electrophile in orange here, right? I've connected these two molecules together. The alpha carbon of one connected to the carbonyl carbon of another. All right? And just like we've seen before, the next step, it's going to be done in some aqueous-based solution. So we get to just protonate that oxygen. Okay, I'm going to be lazy and just draw it. I think we're all well aware of how proton transfer steps work at this point. Okay? And so this product right here is what they call the aldol. The aldehyde and the alcohol all in the same molecule. All right, and so this reaction here would be an aldol addition reaction. Even if you used a ketone, they actually still call it an aldol. All right, it's kind of just a slang term. It turns out that aldehydes way more favorably form aldols, so that's probably why they win in the name battle there. But yes. All right, so these reactions here, not unlike Grignard's or really any reaction that creates new carbon-carbon bonds, are a little bit tricky because we get a big, ugly product on the other side. We start with something nice and small and simple, but then we join them together and we get something big and ugly on the other side. So not keeping track of carbons or connecting things in the wrong way is really, really easy to do, all right? So these reactions, mechanism-wise, you can see, not too bad, pretty straightforward, right? But as soon as we get to bigger, ugly molecules, they can be a little tricky. So let's just practice real quick drawing products. We don't need to draw the whole mechanism or anything like that. I mean, you certainly can if it's going to help you out, but let's just figure out how to draw our aldol products here. Actually, I should be good. I'm pretty sure that they like to do this in ethanol. Okay. I'm going to swap these orders. The top one's a little bit harder. Let's start with the easier one. Okay, but yes, everybody just take a minute and draw me my aldol addition products here. so I think that most helpful way to do this is to draw a second one of your aldehydes and ketones so that you can just kind of make note that you're going to be connecting, again, the alpha carbon of one of them to the carbonyl carbon of its neighbor. Just kind of putting them both down there kind of helps you see it a little bit easier. All right, and I'm going to start by redrawing my nucleophile, right, the one with the alpha carbon. And then I'm going to make that new bond. And when I make my new bond, necessarily on the other side here is that carbonyl carbon. Okay? Now, importantly, when that alpha carbon reacted with that carbonyl carbon, it created an alcohol group. And then I have those other two carbons pointing off of there as well from my electrophile. As always, when we're making these new carbon-carbon bonds, counting carbons is going to be an easy double check. So 1, 2, 3 carbons from my nucleophile, and 1, 2, 3 carbons from my electrophile. Okay. There's another little quick double check that you can do to make sure. So count carbons, all right? Another quick double check that you can do is in these molecules, you always have these two functional groups, okay? Because it's necessarily the alpha carbon reacting with the carbonyl carbon, there's going to be this set spacing between these two functional groups. If we start counting at that alpha carbon, or at that carbonyl carbon, my other functional group will always be located 3 carbons away, right? You will always have that 3 carbon spacing in these aldol addition reactions. And we're going to see a lot of similar reactions, so it's a helpful rule to keep in mind. All right, so before we move on here, everybody double check your second product. Do you have the correct number of carbons, right? Do you have 12 carbons, double what we have in our current reactant? And do you have that 1, 2, 3 carbon spacing between your functional groups? All right, so I'm going to redraw my reactant a second time here so I can make note that it's this nucleophile, this alpha carbon, that I'm going to connect to my electrophilic carbonyl carbon in my neighbor. Okay, I'm going to start by redrawing my nucleophile, and when I draw in that new bond, that means on the other side has to be that electrophilic carbon, my carbonyl carbon. All right, that has this whole ring structure attached to it, another 6-membered ring here. As well as my carbonyl oxygen, which is now an alcohol group. Okay, so again, our two checks. I have 1, 2, 3, 4, 5, 6 carbons from my nucleophile, and 1, 2, 3, 4, 5, 6 carbons from my electrophile. And I have these two functional groups spaced 1, 2, 3 carbons apart from one another. All right. So these were called aldol addition reactions. Okay, there's another very closely related reaction that we can do if we take this exact same set of reactants, our base with our proton source, but then we also add heat. Okay, and so we'll get our aldol addition product. But with that addition of heat, we're going to see a dehydration reaction occur as well. Okay, so if the other one was our aldol addition, this one is our aldol condensation. Our aldol condensation is just our aldol addition plus heat, and this leads to a dehydration. So by dehydration, I mean I'm going to lose a water, right? That's what dehydrations are. So I'm going to lose this OH group as well as a neighboring hydrogen, totaling up H2O. And these dehydration reactions produce double bonds, or how we produce alkenes. So in my dehydration reaction here, so first of all, I could have two potential products. Let's take a look real quick at those two products and see if we can't figure out which one is going to be our major product. Okay, so I could have my double bond form over here, or it could have instead dehydrated in the other direction. I have my double bond formed over here. Okay, we're only going to get one product here. So I want everybody to take a look and try to tell me which product we think is going to be our, which one of these molecules we think is going to be our product. The one on the left or the one on the right? So it is the one on the left. Why is it the one on the left? So I think a lot of people are tempted to say substitution. It's not a substitution argument. There's something more special about this double bond on the left. We learned about this in the very first chapter we covered this semester when we have these double bonds that are spaced out in this perfect way here. Starts with a C. No, conjugated. They are conjugated, right? So now if we form it on the other side, we have these conjugated double bonds. In fact, we already had a special name for these, full circle moment. We talked about these earlier. These are our alpha beta unsaturated aldehydes and ketones, right? Our enones. So our product of our Claisen condensation, we first do the addition, and then at the end here we get that alpha beta unsaturated, in this case ketone, what we called enones as their sort of slang term. Okay, so for the sake of practice, let's do it with our second reaction here. Let's start out with the same set of reactants, but now I want you to give me the dehydration product as well, or rather our condensation product. Okay, so you want to start with your addition product, right? That's always going to be the first step. But now we have this double bond that's formed that's conjugated to our carbonyl group. Okay, and let me just get rid of all these little markings for a second. Okay, and let me make a point here. We've talked about how we can make sure that we have our correct molecule by counting carbons and the spacing of those two functional groups. We'll see the same thing here. In our condensation product, that double bond should always be located between carbons 2 and 3, right? You're numbering your functional groups to make sure you have that proper spacing. Same thing we'll see with our condensation product. Okay. Um, the last thing we're going to do is to talk about now these same sort of phenomena, this alpha carbon chemistry, but this now is under acidic conditions. Okay. And it revolves around what's called an enol ketone tautomerization. Ketoenol, rather. And I know that everybody was just like, oh yeah, tautomerizations, totally. Yeah, I fully remember what those are. But just to remind us here, a tautomerization is this intramolecular rearrangement of atoms. So if we take any aldehyde or ketone, okay, and again, now we're talking about reactions. The previous reactions we talked about were with bases, creating those enolate ions. Now we're talking about reactions under acidic conditions. And under acidic conditions, our ketone is in equilibrium with what's called an enol. If we just pick this name apart real quick, enol, what do we think the en means? A double bond, specifically a carbon-carbon double bond, like in an alkene, right? And what about the ol? Alcohol. And so this is an enol with an alcohol group located next to a carbon-carbon double bond. Okay? And let's just convince ourselves, we said that this was a tautomerization, an internal rearrangement, which means that the molecular formula of both of these better be the same. I'm just mixing up who's bonded to who, right? So in this molecule over here, my ketone, I have 3 hydrogens on each carbon for a total of 6. So this is C3H6O. On my enol, I have 1, 2, 3 hydrogens on this carbon. I only have 2 on this one, but then I also have my alcohol hydrogens, so 6. So this is also C3H6O. Right? So then what's changed here? What bond was broken in this reaction that formed my enol? Yes, I have this carbon-oxygen pi bond that was broken, right? What other bond must have been broken, though? Yeah, I had to have lost one of my hydrogens over here as well. And then I would have formed, on my product side, an oxygen-hydrogen bond and my new pi bond over here, right? But we're just sort of rearranging within this molecule who's bound to who, which is again called a tautomerization. All right, so this again takes place under acidic conditions. I want you guys to take a few minutes here and see if you can't give me the mechanism for this ketone enol tautomerization. Okay, let's just remind ourselves, under acidic conditions, we can always default to, as our proton donor, the hydronium ion, and as our proton acceptor, water. All right, so see if you can't come up with the mechanism for this ketoenol tautomerization. All right, so as we've seen several times with these acidic condition mechanisms, this first step here is going to be a protonation step. We're going to protonate that ketone oxygen. That makes it even more ready to accept that pair of pi electrons in my carbonyl bond. So then the next step, the last step here, because this all happens all in one shot, is now my proton acceptor, my base in this reaction, is going to grab this neighboring hydrogen. Okay, this pair of electrons will come down to form that carbon-carbon double bond and kick that pair of electrons up onto that oxygen. And this is what forms my enol. Okay, so there are some reactions that take place under acidic conditions at our alpha carbon, and it's because of this enol intermediate here. Okay, and so the last reaction we're going to talk about today is this alpha carbon halogenation. Okay, and specifically under acidic conditions. All right, so if we were to take an aldehyde or ketone, let's use a simple aldehyde here. Oops. And we were to combine it, again, under acidic conditions with bromine. Okay, we're going to see a reaction at our alpha carbon, and again, to better understand this, the first thing we're going to do is we're going to draw that enol that we get under acidic conditions, because that's actually going to be our nucleophile in this reaction. So everybody take it a second, given the structure of this aldehyde, draw me my enol. Alright, so importantly now, I have this double bond next to that alcohol group. Okay, and again, we're going to see our enol is a nucleophile. So this is going to react with that diatomic bromine. And what we're going to see is that pair of electrons in that enol double bond is going to play the role of our nucleophile. Okay. And when that happens, that pair of electrons gets taken away from that carbon. So our pair of electrons on our oxygen atom are going to come back down. All right, so we've reformed that carbon-oxygen double bond. But now we've also brominated that alpha carbon. Okay, we still have, because of that protonation step on our oxygen, we still have that hydrogen. So we're going to have to do one last proton transfer step. Leaving me with my brominated alpha carbon here. Okay, so again, these alpha carbons can play the role of nucleophiles under basic conditions because we can deprotonate them, but they can also play the role of nucleophiles under acidic conditions because of this keto-enol tautomerization, right? And specifically, if we have this ketone under acidic conditions and we look at its enol form, we can see that that double bond plays the role of a nucleophile, allowing us to brominate that alpha carbon position, or halogenate that alpha carbon position. Cool. All right, we're going to continue talking about alpha carbon chemistry next week, but we're going to stop there for today.